This is the Mathematics Education Podcast from mathedpodcast.com.
Welcome to the Math Ed Podcast. I'm Michelle Cirillo, an associate professor from the University of Delaware and a guest host for this episode. Joining me in Hamburg, Germany, at the ICME 13 conference is Michael de Villiers, an honorary professor in the School of Education at the University of KwaZulu-Natal in South Africa. He is also co-editor of the journal Pythagoras and an active contributor to the International Congress of Mathematics Education. Michael, thanks for speaking to me.
Hello, Michelle.
Hello.
Nice to be here.
So let's just get started with a question about how did your career in mathematics education begin?
I suppose the easiest answer is to say I was pretty good at math in school, ending top in my class, both in primary school right through high school. I think, to be honest, my choice of choosing mathematics education was largely influenced by some very good math teachers that I had. And also, it may surprise you, because I was good in sport. And I thought that being a mathematics teacher would be the ideal combination of my intellectual interest in mathematics, but also being able to then play tennis and coach young people. I was motivated in a sense because I thought that that would be a nice combination to study.
What were some of your most memorable aspects of graduate school, and what was the focus of your dissertation research?
I think the most memorable events of my graduate work was that I was immediately involved with the University of Stellenbosch experiment in maths education in 1977-78, which was a geometry curriculum, experimental curriculum that was developed to focus more on the processes of mathematics. You may recall during that time there was a large emphasis on the distinction between the processes and products of mathematics, and particularly influenced by the von Hiller theory and Freudenthal. This curriculum was devised to move away from teaching geometry in the traditional axiom, definition, theorem approach, but to have it slightly more problem-centered, as well as to engage learners in defining concepts in geometry, in classifying the various geometric figures, and to actually engage them in axiomatization as well, helping them understand the nature of axioms. Now, this project was implemented in over 40 schools in the Cape Province. It had a control group as a means of comparison to see what gains there were in the objectives, aims that we had for the course. Although the education department insisted that we evaluate their proofwriting abilities to see that our new approach would not make them less competent in proofwriting. And I think the experiment was largely successful, showing that one can have gains in them understanding better the nature of definitions, the nature of axioms, and also improving their ability to define concepts for themselves, and that there was no negative effects in terms of their proofwriting ability. So I think that was probably the most memorable. If I may add, sorry if I talk a little bit long, I think some of the other things that we focused on in my graduate work was mathematical topics, some of which I had not encountered before. Unlike many math ed courses nowadays in the postgraduate level, where there's no math content, we did a lot of projective geometry, abstract algebra, much of which I had encountered, particularly the abstract algebra, but not things like projective geometry I only learnt in my graduate school, nothing undergraduate. And then I think your last question was what was the topic of my PhD. That was, to translate, it was written in Afrikaans. Basically, learners' construction of meaningful deductive reasoning, proof and related processes in geometry. So it focused, it was from there that my model, as it were, for understanding the functions of proof, that proof has various functions that go beyond just a normal verification function.
Thank you. What has driven your passion and work in the area of dynamic geometry software? And what progress have you seen in this area? What potential still remains?
I think what struck me at first about dynamic geometry was how powerful it was as an experimental tool. I have to be honest that my interest in it was from two perspectives. The one was from the perspective of using it as a tool for my own geometric investigations. In one of my earliest talks, I describe how many years ago I conjectured some generalizations of Van Elbel's theorem, which is a theorem that dates back to the late 1800s by a Belgian mathematician called Van Elbel, that if you have a quadrilateral and you construct squares on the sides and the centers of the squares on the opposite sides, those segments are perpendicular to each other, orthogonal, and they are equal in length. Now, the generalizations that I conjectured, I won't go into why I conjectured them. I had some theoretical ideas why I suspected it to be true. I then took large pieces of paper and made paper and pencil constructions, a few, but it wasn't entirely convincing to me that it held in all cases. And I remember the first time with Gabri, I had access to Gabri at that time, or a little later, some years later. It was in the early 80s when Gabri came out in 1989. I made a construction with Gabri, but that was the first edition of Gabri, which didn't allow me to make an easy construction where I could change the shape of rectangles, similar rectangles on the sides, or similar rhombi. And I was still not convinced that it covered all cases. And it was only about a year later that I met another colleague who had then the facilities, and Gabri also has the facility now, to be able to vary the shape of the rectangle and of the rhombus and so on. And after sufficient dragging around of that convinced me that the result was true, and that conviction set me off looking for a proof, which I then subsequently found for both cases. And so it was very much a personal need I had at that time to first gain conviction, unlike the fairy tale people tell at school that, you know, you must first prove it before you can be convinced. I first had to become convinced that the result was true before I wanted to spend the time on finding the proof. And to me that was almost Archimedes' eureka moment to see that they were actually true. And I wasn't going to waste my time trying to find a proof of something that may not generally be true. So I think that was, from a mathematical point, that was very important. But I think that obviously that has strong implications. I think it carries over into education. I think the ability to make a construction and drag and check a number of cases, even special cases, is what makes dynamic geometry so powerful and so appealing. And I think the software is developing rapidly. They're adding new functions to it. There's more slick integration between the geometry and the algebra in all the systems. And even the opportunity now to do 3D geometry is becoming much more possible, which is really hard sometimes with physical models to do the same sort of dynamic geometry and dragging. So it's a very exciting time we are living in.
Is there anything else that you would still like to see come out of these kinds of softwares?
I cannot immediately now think specifically. I can think of areas of research that I think need attention. I think much of the software, if we take Abri 3D that I have been working a little bit with, is probably the best 3D software available, which uses a very intuitive synthetic geometric approach rather than the coordinate approach to a large extent that GeoGebra is using, or even other software. However, it is not always easy to do computations on it, for example, like in Sketchpad, which has a little calculator available. So I think some of the software can be improved by the gradual addition of additional features that can make empirical experimental investigation much easier, so that you can see whether something is continuously changing and which things remain invariant. But I think by and large, most of what is there is already pretty good. I do know of Chinese software that I've not worked with that actually produces proofs, which obviously challenges in a way our conception of proof and what is needed. I still think the human element is necessary. The computer cannot do everything for us, and I think it won't change what we as teachers need to do to help students see proof as a meaningful human activity. I'd hate to see proof completely computerized. I think that is the one thing that at the end of the day we have to sit down with paper and pencil, but it is really a powerful tool on the part of conjecture and experimentation. Cinderella is there that allows one to switch from Euclidean geometry to spherical geometry, as well as hyperbolic geometry, and it is programmable. So it's almost the sky is the limit in Cinderella, although it is perhaps not as user-friendly. So some of the software could maybe become more user-friendly, and I think if there is perhaps more interaction between the developers and classroom practice, that might help. Feedback loop.
I'm speaking with Dr. Michael de Villiers from the University of KwaZulu-Natal about his career in mathematics education. Some of your most cited work has involved the fact that proof can do much more than simply to verify the truth of a claim. And you talked a little bit about this before. So tell us about how you came to those ideas and what influence have those ideas made on research or practice.
Okay, yes, I earlier spoke about the episode of Van Elbel's theorem and how I discovered those generalizations empirically and how I needed conviction before I felt compelled to develop proofs for them. In terms of my theoretical understanding of proof, it goes back to the work of other people. To quote Newton, you're standing on the shoulders of giants before one. And it is ironic, in the US, I have heard people speak of de Villiers' model of the function or the role of proof. And it is a little bit embarrassing because I can't take full credit for it. People like Alan Bell, he was probably the first person in one of his papers in the 1980s already. Alan Bell distinguished between the verification, explanatory, and systematization function of proof. But even if you go back to the old Greeks, frequently reading from the lens that I have, if you read works by even Pappus, the famous Greek geometer, he talks about explanation and verification, and it's quite nice to read these ideas recurring in the writings of mathematicians. Davis and Hirsch the mathematical experience also make the distinction between verification and explanation. They have a long discussion about the Riemann conjecture, about even if we had some machine that could verify, Rav, another mathematician, makes the same. If we had a machine that could check and give us an answer, yes or no, the Riemann conjecture is true or not, that's irrelevant. The truth value doesn't matter. It is understanding why it is true is the quest that we're after. So my ideas, I don't think, are so new, these distinctions of proof. I've added a few, like the discovery function, the communicative and social aspect, I think, of proof I've added. And then I've perhaps elaborated these functions of proof, maybe more than any of the other predecessors have. And what I've tried as a lifelong work, try to develop activities to try and get these meanings over to students. And some of my students, research graduate students, have also designed their research around activities, task-based activities and interviews with students to see whether one can be successful in getting learners and students to understand these meanings with reasonable results, I would say, so far.
Is there any influence that you'd still like to see related to that work?
Yes, I'm pleased to say that particularly my 1990 paper on the role of proof is referenced fairly widely in the area of proof. It has had some influence, although I would say predominantly, if one looks at research on proof in the last 20 years, predominantly the focus still is on the verification function. And I do feel that is a problem, particularly in dynamic geometry. I think the verification function is very easy to get the idea across to students within the context of number theory and algebra, where there are many examples that I have used myself, to get them to get learners to understand that you can have vast amounts of empirical data that support a conjecture, but it can still turn out to be false. Within dynamic geometry, the situation is a little bit different because you have a continuous transformation of a figure across the screen, and it is very difficult to find good examples to show students that something that appears to be true in dynamic geometry and passes the test, that it actually turns out to be false. So to motivate the function of proof as a means of verification is much harder in dynamic geometry, which is why I have argued for so long that researchers ought to focus more on trying to develop and focus on the explanatory function of proof. Research that has been done by my students have indicated that quite often learners are convinced that something is true by dragging. You know, they say, I have 100% faith that this is correct. And we know that from a lot of research on proof. But when asked if they want to know why it is true, they often say yes, you know, and they say, that would be very nice to know why it is true. Then they respond positively. And I think teachers and researchers have not sufficiently latched onto that as an avenue of research. I think my wish would be to see more research of that kind and also curriculum materials developed to try and develop that aspect, as well as the discovery function of proof. Now, more recently, I know in Scandinavia and in some of the Eastern countries, there have been groups of researchers that have been developing and written research papers on the discovery function, and even theorized, developed my model even further, which is good, on what do we mean by the discovery function of proof and how can we attain that with learners. It is slightly more advanced, but it links to Polya's looking back on a proof and leading perhaps to specialization or generalization of a result. because the proof gives you insight. Why something is true. Now you can go to town, you can specialize, you can generalize, and so on, something that might not have been apparent by just dragging around on the screen. Regarding the verification function, I do think it ought to be addressed, but there are very few examples. I have in my Rethinking Proof book, I have a few deliberately contrived examples that are pedagogically contrived examples that I designed to deliberately mislead students to make a mistake of making a false conjecture. The way I did it was to set the accuracy of a sketchpad, which is what we were using there, to only 1 decimal accuracy. And the particular conjecture remains true, survives the drag test when you only work to 1 decimal accuracy. However, the falseness of the result only becomes apparent when you look at it to 3 decimal or 5 decimal accuracy. So, but these are slightly contrived examples, but I think those sort of things do raise the issue, because computers can only calculate to a finite number of digits, finite accuracy if you like. And it does raise the issue of, can we be really 100% sure? I have a better example that I found out 2 years ago, actually from some of research. A colleague and I were doing a mathematical result that is probably too hard for school level, but maybe for teacher training, about points being collinear. And we discovered 2 results about certain points being collinear that I won't go into now. And we dragged it around and so on, and we were pretty convinced that it was true. We couldn't see any counterexample on the screen, and after spending some time unsuccessfully trying to solve it, it started dawning on us, maybe it wasn't true at all, but we couldn't find a counterexample. And then the obvious idea, which I should have thought of earlier, was that we should zoom in and use the enlargement facility of the dynamic geometry software. But it required a zooming in of 100 to 1 before it only became apparent that these points were actually not lying on a straight line. So that is really... That's really pushing the limit, and again it raises the issue. I mean, if you have to zoom in 100 to 1 before you actually see it, then at some point the computer can't zoom in anymore. So you can never know with absolute certainty that the computer's software is not making a mistake. So I think one can get to that, but that is far more subtle and I think more sophisticated for maybe more mature students. I don't think it is feasible to get a meaningful understanding of the verification function in dynamic geometry, or not as easy as the explanatory and even the systematization function as well.
This discussion is making me think about the work of Dan Chazen, where he found that students were fairly convinced by dynamic geometry software and actually thought that that was a proof.
Yes.
Once they did things past the drag test and they saw with many examples that something was true. Do you have any suggestions for teachers or educators to prevent these kinds of misconceptions and to motivate students to go further and try to find a proof?
Well, this is where I would suggest that we actually, particularly in the introductory phase of proof and working with student teachers, we focus on the explanatory function by asking them, well, why is it true? Can you explain why it is true? To stimulate that need for understanding why and to create that need. And then to lead and guide them in the direction of a proof that actually explains the result to satisfy that need. I think Cirillo recently published a paper on intellectual needs. And this is dealing exactly with that sort of intellectual need. They don't have a need for verification, but and our research certainly supports that, they have a need for understanding why, which is something different, and we need to focus on that. my suggestion actually is that, particularly with learners in the high school who are first being introduced to proof in dynamic geometry, specifically, is perhaps to avoid using the word proof, because in everyday language, proof means to verify, to make sure. I would suggest use the word explanation, and perhaps just to say logical explanation or maybe deductive explanation, to add to it, to say that it's a little bit more than, a non-deductive explanation, because you can also have explanations that are not what we call proofs. But I do think it is an important issue. There's no getting away from the fact that they find the software very convincing. That's why I suggest switching it to something else, and particularly if you could choose an example where by giving a proof gives insight into how the result can be generalized. One of the examples I use in the Rethinking Proof, also designed pedagogically, I start off with a right triangle with equilateral triangles on the sides, and the outer vertices of the triangles on the sides connected with the base triangles opposite vertex, and those lines are concurrent. And then here we have a situation. We see it's true. Why is it true? And if we then develop a proof, it transpires that we never used the fact that we never used the right angle there. So immediately you can see it generalizes to any triangle. Now this is the Fermat-Torricelli point. But the sequence is designed to show them that, if you develop a proof, now you understand why you look back on the proof in Polya's style, you can see the right angle was never used, so it immediately generalizes. And I think if we can design more activities at various levels, even in the primary school, there are some simple cases one can do. I know some of the Norwegians have found some success at fairly elementary level. The example I'm giving is probably more advanced. So I think it is possible. One can develop some understanding and appreciation for the fact that if we have a proof, it tells us more than just knowing the result is true, because that alone is not very useful.
You've also done quite a bit of work on defining, which I've recently been reading quite a bit of and enjoyed very much. You've been advocating for students to participate in developing mathematical definitions rather than just being given definitions by their teacher. You talked about that a little bit, that in the sense that work began in the 70s in your
Correct.
Part of your doctoral work. Could you tell us more about that work and how it's evolved?
Yes, you are correct. My interest in defining and axiomatizing as processes started in the 70s. Subsequent to that, perhaps that you might not be aware of, is that I also developed a book called Boolean Algebra at school, which focuses on the processes of modeling. Rather than presenting Boolean algebra as is normally done, usually at university level or in a computer science education course, they start off formulating the axioms and then proving the theorems after that. Starting from the context of switching circuit problems, which I have done, in fact, my first as a beginning teacher. I was postgraduate. I already had a degree. I was then doing my teaching diploma. One of my first lessons, critique lessons, or whatever they are called, was in fact with Boolean algebra, not geometry, where I basically started off by giving these problems to learners, and they actually had switches that they had to connect up and solve various problems. And the idea was to start with a real-world problem and then to develop an algebra for switching circuits, but purely by abstraction and generalization of that, not as a finished structure. However, after we had done quite a bit of work with that, then we asked the question, well, how can we now organize this into a structure, referring to, for example, Euclid as a model of a deductive structure starting from assumptions. And then students were led into starting to systematically examine the logical relationships between various statements, coming to the conclusion that there are different alternative sets of assumptions, axioms we can choose from which to derive Boolean algebra. So that had a strong influence for me even in geometry. I think it is a big mistake. It's almost a sin, to quote Freudenthal and Blanford, who wrote in the beginning of the century. It is a sin to present students with a ready-made concept via definition. Of course, one cannot have them reconstruct every definition there is in the curriculum, and in mathematics at some point we have to switch over to a more direct approach. But I think there should be some opportunities for learners to engage in defining concepts. And I think it is important to distinguish between two processes. The process of a posteriori defining, where we define a concept after you have come to know it for some time. An activity I often do with teachers when I talk about definitions and defining is ask them to write down a definition for a table or a chair. They all know what it is. It's a concept that they've known all their life since a young child, but they struggle with it. How do you define it? Do you define it in terms of its function? Do you define it in terms of its shape or its utility? And they argue and debate a bit, but eventually some consensus is reached about what important features have to go into defining the concept of a chair or a table or whatever the case may be. Now, this is a good example of descriptive defining. In mathematics, people make the mistake that they feel children will only learn if we start off with a precise definition. But we know from the psychology of learning theory, and particularly the vanilla theory as well, that very young children are visual. They are not going to understand the definition. It's not at the level of understanding yet. So it is useless, in a sense, to introduce a square as so-and-so quadrilateral with these and these properties, because it would not be sensible to them. So I do think it is important to realize that in order to understand definitions, they already have to be at Van Hille level 3, to use the American numbering system, and that the focus initially should be in building up a concept image, a visual concept image, firstly, seeing many different versions of a rectangle, long, and even when it becomes a square, etc., to build up the visual, which is Van Hille 1, then to start learning the properties without giving a formal name for it. Nobody learns what a chair is. We don't teach our children, and certainly I wasn't as a child taught a formal definition and memorized a definition for what a chair is. You don't have to memorize that for a square either. They can build up a sound concept image of what a square is. And then when they've reached Van Hille level 3, then you can start asking the question, well, can we not choose one or two of these list of properties as a defining property of a square? And I think in exploring that, it is important that learners be given the freedom to come up with different versions. Also combating the misconception that students often have that there's only one correct way of defining a concept. As we know, there are many different ways of defining it. And I think that is a valuable educational experience, that sometimes we choose definitions in a particular way because it is more valuable than another. If you just give them the definition, they don't get that experience. So if they can argue and debate a little bit in class. And part of that was also included in my PhD. Now, I myself haven't done much research since my PhD on that, except that I was continually during my teaching working with prospective math teachers, incorporating many of these ideas in my own teaching and with professional development. And some of my graduate students, like Rajan Govender, his master's, working with student teachers, prospective teachers, on developing understanding and engaging them in defining a rhombus, which to them was a sort of a semi-familiar concept, although many of them had vaguely some years ago just been given a sort of a textbook definition, but he took them sort of gradually through a Van Hille structured learning activity to have them come up with a variety of possible definitions for a rhombus. So it is possible to achieve. Obviously, one cannot do that even with all the quadrilaterals, because it is time consuming, but I think one should at least choose one or two examples, because I think once learners have seen where definitions come from, that they are not just handed down by the god of mathematics, as it were, that is fixed in stone, I think they understand it more as a human endeavor rather than something that is thrust upon them, and that we can make choices. In fact, in one of the aspects of my PhD was in a classroom we tackled the issue of hierarchical versus partition definitions, or what I often say is inclusive definitions and apartheid definitions, where we allowed students the freedom to choose whether they wanted inclusive or non-inclusive definitions. And there was a big debate in class, and some were very adamant they wanted to stick with their non-inclusive definitions. But as time went on, and I of course chose activities that would gradually make them realize that it is very cumbersome and very problematic to use non-inclusive definitions, because it doubles the number of proofs you have to write. Eventually, within a week almost, all the others said, okay, we'll abandon our non-inclusive. We can see the value of having inclusive definitions. And this was in a time before we even had dynamic geometry. So it can be done, but it is a challenge, I think, that is often neglected because people treat it in a very dogmatic, authoritarian way. And it's not just in geometry. I mean, if you open up a textbook, you will find people giving a definition for a prime number. That is not necessary. Students can be given an activity, for example, to find the divisors of numbers from 1 to 100. And then falls out a pattern that you find these numbers that are only divisible by themselves in 1. And in that activity, you can then now say, well, these numbers have a special name. They are called prime numbers, and all of the others can be written as a product of prime numbers. Then you don't have to start with a definition. I mean, that's just a simple example of how you can reverse the sort of traditional approach, definition first, and then the concept image. I think it's the other way around. There's also another aspect of defining, which is constructive defining. Now, mathematicians often create new objects by taking existing concepts and their definitions and then varying them in some way. By generalizing some aspect of a property or excluding or adding other properties, we can define new objects. This is a very typical way. We can see that through the history of mathematics. And I believe learners should also, and students should also be engaged in that. And a good way of doing that is asking them what-if questions. What if, or perhaps asking them by using analogy, if we take a rectangle, we know the properties of a rectangle. It has axis of symmetry, equal angles, equal diagonals, etc. What would be the analog equivalent of a rectangle when we are looking at the hexagons, for example? Or if you want to switch to non-Euclidean geometry, what would be the equivalent on a sphere, etc.? That is an example of constructive defining. How would we now define such a concept and then to explore properties of that? And I think there's value in that, because that's teaching them the way how mathematics develops and how mathematicians think, rather than just providing them with a ready-made product.
What challenges do you think the field of mathematics education should address over the next 5 years?
I think that's a very hard question. I think, from my personal perspective, I think there's some danger of fragmentation of the discipline of math education. It is exciting on the one hand to see so much being developed under the banner of mathematics education, people approaching it from many different perspectives, from a sociological, political angle, and using, of course, psychological learning theory, I think, to me, is one of the cornerstones of mathematics education. There is some danger in fragmentation also. Just as we have in mathematics. Mathematics itself has become so specialized that you have in a corridor of mathematicians of 10, nobody knows what the other person is doing, and I have a fear that mathematics education to some extent is moving in that direction, being developed such a high level of nomenclature, terminology, specialized in some fields, that people approaching it from a different angle, they can't communicate with each other, and sometimes the things that they give very specialized names to are really very simple, like the zone of proximal development by Vygotsky really just means you must be at the level of the child. I mean, why not just say it what it is? Does it make it any more academic or any more intellectual to give it this fancy name? And somebody else might give it a different name. So you have this vast host of different terminology coming on, and it can become a little bit confusing, I think, particularly for young people in the field. So that worries me a little bit. There's some fragmentation of the discipline. I think challenges facing math education, of course, is the increasing availability of software of all kinds, not only dynamic geometry. It's now available on the smartphones, even applets that can do all the algebra that they do at school. These are challenges I think we are only starting to deal with. We can't ignore it. We are living in a technological society where children have access to these, our students have access, and it is our educational duty to incorporate it into the classroom and use it to the benefit of learning. And I think these are issues that we will, in an exponentially increasing way, have to grapple with. I think the last issue I think that we need to deal with is teacher education. I think worldwide is in every country there is concern about the quality of teacher education. What do they need to know? How strong, the PCKs and the MCKs, although there I'm using terminology again, but you know what I mean. These are issues, exactly, how much mathematics, what kind of more advanced mathematics do they need? What should they know about learners' intuitions that they bring to the classroom, their misconceptions, how to deal with them. There are many issues around here. I know work is being done in that area, but I think increasingly more so in future.
Final question that you don't have to take too seriously. If you had not worked in mathematics and mathematics education as a career, what can you imagine yourself having done instead?
This might shock you, a professional tennis player. When I finished at school, I was offered a 2-year contract by Adidas to play in Germany. This was in the early 70s, which in some ways I regret not taking up. But professional tennis was then in its infancy, and I didn't then foresee how it would develop later. So I have some regret maybe not going that route. I thought it would be the more cautious route to first go and study, get a degree, finish that, and then perhaps go overseas. As it happened, that never happened. I did play tennis at a very high level. I was ranked, my highest ranking was number 4 in South Africa. I have played against Davis Cup players and had some wins as well. So I've had some success, but I was never on the tour. So it might have been nice. The other thing I would have liked to do, been to be a successful writer of novels and poetry. And perhaps now that I'm retired, I might get time to spend on... I have published poetry, in fact, but perhaps do some more poetry, and I'm not sure that I have the energy to write a novel. That's hard work. You have to do a lot of... It's like writing a thesis. Anyway, those are my interests.
Do you still play tennis?
I still play tennis, not competitively. I had major back surgery some 10 years ago. I played in the seniors level tennis, and it would have been nice to play more on the international seniors circuit. But with my back surgery, it is best not to play anymore. I mean, I still play, but not competitively, at least socially. Well, working mainly with young players. I still do some coaching and play about 2, 3, 4 times maybe a week for an hour, hour and a half. So I'm still fairly fit.
Thank you for taking the time to speak with us about your work. This is Michelle Cirillo for the Math Ed Podcast. Sam will be back for the next episode.